thanks, it's wonderful to be here. I don't have a present, but I try to explain something. So we're mixing two things, graph writing in a broad sense, and mean field approximations, which is something that comes from statistical physics and is used, as far as I can tell, on a wide scale to simplify the description of complex dynamics, typically microscopic stochastic dynamics. And so the kind of deal we'd like to arrive to is if you describe your system as a continuous time Markov chain on some kind of graph-like structure, we'll generate this kind of approximation for you. We'll generate it, we'll not tell you how good it is. This is complicated, hairy mathematics, and actually mostly not known. But we'll do the algebraic generation, so we're solving the algebraic part of the problem. So just two little remarks before I start saying anything serious. The graph is a state, right? So what the continuous time Markov chain does is take a graph and modify it in a simple way to obtain another graph, and that is stochastic and time continuous. So we're rewriting graphs. So the graph is the dynamical object itself. It's not dynamics on graph, although we can also do dynamics on graph. So we can do both. And by graph, I mean really graph-like. So it can be typed, it can be hyper, it can be directed, it can be multi-edges. It's a graph-like structure, and the technical way to talk about this is in the framework of adhesive categories and variants and linear Sesquier-Bouchard rewriting. But I'm only going to talk about graphs. But that gives you tremendous syntax independence, if you wish. So that's what we're looking for. So I'll start with a bunch of examples. So where we actually find people writing on an ad hoc, case-by-case basis, this kind of differential equations that are supposed to capture something of the system. So people do it in social networks. I'll show you an example. People have been doing it since centuries on petrinads, also known as chemical reactions. And this is the case of discrete graphs, so it's a trivial subcase of what we propose. And people do this in toy models of statistical physics, not quantum physics, or statistical quantum actually. And so an example here is the totally asymmetric exclusion process, which has a vast literature and which falls inside our net. How wide the net is, we have yet to discover, but it seems to incorporate, to capture definitely something physicists like to do. Example. Number one, in a recently published paper, Dorat is not a physicist, but a mathematician, was trying to come up with clever probabilistic stuff about a graph fission model. So you have a type graph, nodes have two colors, blue and red, and they're collectively trying to either reach a consensus or divide and not talk to each other anymore. So you have two potential evolutions here each time. You pick up a connection between a red and a blue node, and the number of such connection is going to be that capital N10. So 1 is red, 0 is blue. And either one of the two nodes managed to convince the other node to flip its position, so to take the color of its neighbor, or, and that is with probability alpha, they just don't talk to each other anymore, and one of them uniformly at random rewires to any other node in the system. So this mixture of flipping the state and flipping the entire graph, or flapping an edge, and flip and flap an edge in the graph, that's conducive to a very interesting and complex dynamics. And the paper, just if you ask, is not actually getting to any exact mathematical result, but there's beautiful heuristic maps around this system, which itself come from physics, from Mark Newman, and that kind of statistical physics applied to networks. The point here is 3 pages in the paper, they write that differential equation. So it's late at night. I was like, come on, we're also writing differential equations for graphs. I'm sure it must be the same. And I checked it out. So I applied that formula that we had for our own formalism to this thing, and it's exactly the same formula. So I discovered that time that surely what we are doing for side graphs, kappa, the language we're using to model biological systems, has actually very little to do with kappa, and everything to do with graph-like objects. So we decided to go on and do graph-like objects. And it turns out that I'll not mention it again, but the workaround and the abstract route which goes through adhesive categories actually is very convenient. Even if you only wanted to prove and to generate these good equations for graphs, you'd be better off doing it in an abstract way, which is quite fascinating, because it encapsulates combinatorial stuff that I cannot discipline just with my intuition. I have to have a methodology. Alright, so that's one example. Another example from physics, straight from physics. This is you can imagine a piece of DNA and a walker with 2 feet that's working on DNA, and it's seen from above, right? So that guy can move his left leg or can move his right leg backward. It's a reversible walker. It's got translational symmetry. The mark is infinite. There's no boundary condition, the backbone, and all sorts of parameters. So it's a microscopic system. And the formula below, which is the main item in this spiral paper, is describing the mean velocity of the engine along DNA. We look at it as a graph writing system, and we just press the button and we obtain that equation. So the button I'm going to try to describe now. So these are examples, right? This is just a little interlude to tell you that, so this is another view at the 2-legged objects, to tell you that sometimes you don't want to replace altogether your macroscopic system with a deterministic limit, but you want to keep some of the stochasticity. So there are intermediate objects called stochastic differential equations that will do this for you. And this is a 2-dimensional Ornstein-Uhlenbeck, so mean reverting process. And you see that the 2 legs are moving along the bisecting the x-equal line here. But they are moving in a kind of in a fuzzy way. So they globally have a motion which is actually down one here. And so in the deterministic approximation, we'll forget about this and we'll look at this trajectory as a single deterministic trajectory down this line. So this is doing 2 things. It's a vivid illustration of the fact that there are other intermediate approximations that can be more informative, and it's also a way to say that I'd be interested to try to find out if we can find them by the same type of machinery, but we don't at the moment. Okay? The relationship with Prakash is the following. I've learned my probability theory of Prakash for one thing, and I've also rekindled the desire to do continuous mathematics. So, that was my way out of proof theory. Anyway, so a little generic piece on continuous time Markov chain on a countable state space. So we have an observable f, which is just here a map with no particular structure that maps the state to a real number. Very easy. And we can write the master equation or the forward equation, which says that the derivative of the probability to be somewhere at time t is given by the infinitesimal generator of the continuous time Markov chain, which is called Q. The little t is just a transpose, and it's really just a convention. So the thing is, and this is the continuous time analog of the standard thing for discrete time Markov chains. The thing is, I can extract from this a differential equation which is going to describe the mean value of any observables at time t, and the dependency in t is not in f, because f is just a function. It's in the probability distribution p, which is the solution of that equation. So I can compute that together. If I take the derivative of this thing, this is the derivative of this line row vector against this column vector, and this gives me this, because this derivative f is constant, this derivative is here, so I get this. So you see this equation which is well known, and actually exists also for in much more general cases, where Q is seen now as a more abstract object, something of the type typically something of that type. So I write it in this way, but here you can replace this with some kind of L space on some abstract state space. I write it backward because what it's doing, it's QF of x, so what x is in x, is equal to, let's say in the discrete case, is equal to the sum over all the points to which x can jump of the rate at which you jump from x to y multiplied by the delta of f between y and x, between the target jump and the point you jump from. So this is the average change of f as a function of the point where you are sitting at per time unit. So it's the mean rate of change given that you're at x. And this formulation here is just the functional formulation we've been studying for some time with Prakash in the theory of approximating a discrete time macro change. So it's the formalism is completely continuous. Whatever. So that's on that. So I want to introduce two ideas here. Instead of looking at f as being an abstract function of the state, let's look at f as living in a small sub-algebra of this big algebra. And let's assume that we have a linear base for that algebra of functions, which I write b. Then, if every g in b has the good taste of being also in b, or in the linear closure of b, then I can replace this term here with that term. So that's interesting. So that gives me So that's interesting because that gives me an infinite system of, in general, infinite system of differential equations, which is indexed by the linear base of my subalgebra. This is a finite sum, and every time I write the differential equation for a vector or function in B, I can re-express it as a linear. I can express the vector field as a finite linear combination of guys in B. So if you figure it as a big matrix, and you imagine, let's say, typically that B is countable, you have a countable matrix. It's row finite. You have almost everywhere zeros, and it's a differential equation in that state space. Incidentally, we know this linear differential systems, which are row finite, are exactly the ones for which the vector field is continuous for the topology, the product topology, and there's a theorem which says that they have solutions at all times. So we're, whatever we write exists. So I said I was not going to do the maths, but actually this thing exists. So that's nice, but it still means that if you're interested in tracking the mean value of whatever function f, which is in B, or in the linear span of B, you'll still need to track to solve an infinite number of differential equations. So here I'm introducing a second idea, which is that this is a subalgebra, the linear span of B. So why not taking a polynomial base B0, which is going to be polynomially generating, so of which the generated algebra will be the linear span of B. In that case, I can expect every h, which is in B0, for example, to be rewritable as a linear combination, but now the coefficients are indexed by the monomials in B0. Okay, so I place myself in this things. Right now it's not apparent why I'm doing this, but it will become clear in a few slides. Wait, that slide. So this is the abstract thing, and there's not much you can do. You have a subalgebra. This is the set of multisets of a base set, and the transitions are given by reactions. And then I can take, as an example of a subalgebra, the linear span, the polynomial span of the projections. So this means that I give myself any polynomial function into the number of A's, B's, and C's in my multiset. So this is cute because it's both a linear span of the monomials and a polynomial span of the basic projections. So now, we're not really interested in multisets, we're interested in graphs of some type sigma. And we have the exact same analog here. We have another situation where we have a subalgebra of observables, which is generated by a very nice set. So let's look at it. So our subalgebra is the linear span of the number of copies of Z in X. So it's Z is a graph. And you're defining Fz, which goes from graphs of some type into the reals are really to the integers here. And it's defined like this. Fz of x, another graph, is the number of instances of z in x. Right? So if the graph is discrete, it's exactly the same thing as a projection function. If it's not, then well, that's what it is. But you keep this decomposition, and this time you can prove that the sub-algebra, which is polynomially, the polynomial generator of that algebra is given by the fz, where you restrict z to be a connected subgraph. So it's not difficult, and it's key to the proof. And it's an interesting situation. So okay, so why are we doing this? So this is true, for one thing. I'm doing this because the rate equation, which subsumes all the above, has this shape. So I'll detail all the ingredients. This is what we call the mean field approximation for a graph writing system. So I'll detail all the ingredients, and I'll explain them one by one. So this is the differential of the mean value of this quantity, which is actually the same thing as this. So the number of copies of, f in this case, whatever. So this is the number of copies of f in the current state of the system, and this is the average value of this quantity, and this is its derivative over time. So we have a big expansion here, so I'll go through the terms one by one. So first of all, we have a minus bunch of terms, and we have a positive one. So these guys are just instances of f that are consumed by transformation, and these guys are produced. No surprise. Then we have a sum on both sides on the number of rules we have. So this is just saying that we'll consider each rule one by one. Then each rule comes with a constant rate. That's completely standard. Here's something interesting. Here, we're looking at the minimal ways in which we can take the union of the left-hand side of a rule alpha and the particular thing we're trying to track. So this is the structure which we're introducing, which says that if you want to count the number of copies of z into x, and you have the left-hand side of a rule, let's say f of alpha, then you have to look at how you can decompose this thing in a minimal way. So these are the unions of graphs. And there's finally many of them, and it's a phenomenon of multi-colimit. Oh. And here in the category of graphs and graph-like objects, under suitable finiteness conditions, this is going to be finite. So this sum is actually finite. I'll show you a very concrete example in a moment. Alright, so that's one ingredient. The next ingredient is that quantity. So this is mu hat is actually the tip of this minimal cospan that decomposes any cospan, so you find many of them. So we're going to count the number of these guys. And phi is the decomposition of this guy into monomials, or the equivalent of monomials, connected components. Then you have this beta, which is just the multiplicity. So this is just because the map that takes a cospan and maps it to its tip is not injected. You can have repetitions. And this seems trivial, but this is where all the combinatorics is hiding. So, I could never write these coefficients. And then there's a complication here, which actually takes 80% of the proof, which is that here you're looking on the right-hand side, so you have a right here, and you have to pull back the minimal gluing here to the left, because that's what you need to count. And so dagger here is supposed to be the inverse under the rule alpha of the gluing you're looking at in this summation. And finally, there's the polynomial thing, which is that instead of writing, as we should, the expectation of the product, we're writing the product of the expectation, which is the deterministic approximation per se. That's the mean field. And so if I was not doing this, there would be an exact differential equation. And to do it, this is where we need to have this polynomial generating structure, so that we sum of the U's that are in this. And so if you remember the last slide, we said that if f is connected, then we'll find U's that are also connected to do this. So we have a self-consistent set of observables, such that if I want to write the differential equation for any of them, applying this formula will tell me to write more differential equations for people in the same class. So, so if we think of the, I don't know, the talk of Joel this morning, he was computing orbits of points in a finite dimensional vector space under linear transformation. Here we're computing the orbit of f under the jump function q, because of this equation. And we're finding an orbit that is closed if we have this polynomial generating condition, and which is the orbit of the number of copies of connected objects in the system. Sometimes the orbit is finite, and these are very interesting examples actually. But in general, you cannot expect anything better than countable. For Petri-net, it will always be finite, trivially. But there are examples. Alright, so we've seen this. So let me illustrate some of the various ingredients here. I'll show you the main result, which is to show that the basis B, so the observables for graphs, is closed under the jumps generated by any of these graph writing systems. And this is the expression. So I'm not going to try to prove this. This is where you have to work. You recognize the two terms. And then this is the other theorem, which is much, much easier, which says that we can use the connected guys to construct our self-consistent set of variables. So if I go back to the physics example with this thing working on DNA, this is the system we're looking at. Now I have to minimally glue an observable like this one to the left-hand side of a rule, or the right-hand side. So this is this lattice of unions of objects. Most of them are disappearing because we bring invariant arguments. We know, for example, we never have a gray node with degree bigger than 3 or 2, so we can kill some of them. Then we get this expansion. So this is a straightforward application of the formula, but it's still very infinite. And then we bring another type of invariant, which is that in this particle system we don't have boundary conditions, and then we get exactly the equations that the people are writing in that paper. So it's a mixture of this general jump closure result, the abstract way to get rid of moment of higher order, and the normal, computer sciencey way to simplify the description of the dynamics by invariance and reachability. But you do have to put everything together to get the result. So maybe it was not so trivial after all, I don't know. So this is just to finish with what kind of formalism we're really using, because we're working with graph-like writing. So we can either rewrite in graph or some kind of adhesive category with this type of final pullback complement / push-out system, or with more in the style of Glean actually, with single push-out rewriting on partial maps. And we get that the derived CT&C is obtained like this. So we have blah blah blah, some stuff. This is just the beginning of how we can abstract what we have done into something that might be more edible for a theoretician. So we have a double category structure, and we like to be able to really package everything in an abstract way. And I'm done. Thank you.
So, I understand when people in statistical mechanics do mean field approximations, there's some kind of measure there that we use to average some quantity. I didn't really see, we kept pointing at things and saying, that's the mean field. I didn't really get how I should interpret that as a mean field approximation.
So mean field comes from Ising models, right? So you
have many things.
Yes.
Hartree fault.
But I think the origin of the terminology is you replace the field induced by your neighbors by the mean field of So here, the place where we're doing the mean field approximation is exactly here. So we commute. So here we should write the, if you vaguely visualize the development in V0, we get monomials. So we take the expectation of monomials because of that thing here. So we have this expectation relative to the current probability, and we apply it to this thing. So we get expectation of monomials, not of observables. So product of observables. And but then, then we say, oh well, essentially we write this. We say, well, let me write it in the Patronate case, right? So you say, well, the number of A's in my system to the square, that is equal to the mean number of A's to the square. But of course it's not true, right? The difference is the variance of the number of A's in my system. And to switch from here to here, that's the mean field. And if you want to switch a little further down the road, so if you want, for example, to get rid of the polynomials of starting at order 3, you get what people call moment closures. And there are other techniques from the statistical physics that we subsume, like something called pair approximations and everything. I think we're bringing quite some order in this, just by making the syntax explicit, we get that all this confused terminology stands aligned. So that's where the mean field is.
Even simple situations like the embodied problem, which can often be treated through mean field approximation, can you do something like that?
Yes. So no, I think this is good. I mean, not so. For example, when you solve the molecular orbitals of the hydrogen atom, you do mean field, and this is the beginning of quantum chemistry. So no, this is going. So okay, let me draw a diagram to clarify. So this is mean field approximations. Okay, there's a lot. You can do them in quantum chemistry. This is an previously unidentified subset of mean field approximations, which we do now formally. So the formal. And this concerns objects that we can look at as CTMCs over graphs. So they're far from exhausting the, what statistical physics does, hopefully, But so you'll find many of the things that go under the same name and that clearly share an error family. But we're just capturing what I like to think of as a substantial part of what they're doing. So it's more microscopic systems that are, this type of system.
I have a question about the water. So I've seen the lovely videos made by Harvard Biology Department showing this thing dragging a protein behind it.
Yes.
How does it change direction? There's no symmetry about whether it's moving forward or backward according to the equation.
So in the model, there's a quantum of energy that's not represented here that you have to spend if you want to bend the energy landscape and get some kind of mean motion and that's directional. If you don't, then the thing will just be a random walk with some characteristic and will show no direction. So in the real system, what they do is they spend ATP, which you can think as a concrete representation. So the energy in the bomb that you consume each time you step, for in whichever direction you are going, you can think of it as a concrete way to break the translation symmetry of energy in the system. So that's the way nature does it, by spending ATP. But it's reversible in principle. So the fact that you don't go straight to a deterministic representation makes a real difference. And in particular, you can, even if in the end you're deterministic, you can compute the deterministic characteristics of the system as a function of the microscopic little hesitations of your walker and the level of energies of the offset between the legs and everything. So I think that's the point of the modeling.
One more quick question.
So, do you have a handle through this methodology on the error of the mean field approximation, or the kinds of objects where that error is going to be small?
No, I don't even have a handle on state the correctness. I think I'm trying to learn the maths. So, so for example, that microscopic system will converge to the diffusion thing in terms of time convergence or some kind of weak star convergence, and it's very complicated just to prove that it does converge, let alone actually trying to compute the error. I'm not saying it's impossible, I'm saying I don't know the maths. Maybe some people actually, people who do fine stochastic processes actually know how to do this for some systems. I like to look into this actually, but for now it's much worse than not knowing the error. I don't even know, whether in the limit it works. So there are extensions of the law of large numbers, functional version of the central limit theorem that are supposed to do this for you, but I'm just learning them.
For your festival.
Sorry?
We work on it for your festival.